Okay, here we have the next installment. I asked you to do some questions, so on this, I think all I'm going to do is put up what the question was in case you don't have it in front of you, and then how to go about the answer. So the initial setup was we're using Coulomb's law. We have two charges, Q1 and Q2, separated by a distance r. In this case, we're calling Q1 Q and Q2 equal to Q. And if that's the case at a distance of r, the force is 100 newtons. We're going to compare all of these cases to that original case. We may bring that back if we need to. The first case that you had was, how about if Q1 was now 5 times Q and Q2 was 3 times Q, but you kept the distance the same. As you can see here, I wrote down Coulomb's law. You have K, Q1, Q2 over R squared. The bottom stays the same, the denominator, but the numerator, one of these is going to multiply by a factor of 5. So you increase by a factor of 5. And then the other one is going to increase by a factor of 3. But it's the product of the two, so that means it's going to be 15 times greater. So I think the new force, what we're going to say, is 15 times what it was before. So in this case, 1,500 newtons. So the answer to the first one was 1,500 newtons. Next case, case 2. You go back to the original charge. Q1 is back to Q, Q2 is Q, but the distance is twice what it was before. So in this case, the numerator is going to stay the same, but the denominator is going to change. So if R increases, then F should decrease, but by the square of that number. So I think you should go down by 2 squared. So now it's going to go down by a factor of 4. So if you have a force of 100 newtons, you divide by 4, your new force should be 25 newtons. I think the answer to case 2, 25 newtons. Moving on to the next case, case 3. Go back to the original case of Q and Q. Now we have 2Q, 4Q at a distance of 2R. So now both the numerator and the denominator ought to change. So our new force, we're going to have a factor of 2 times as much for the 2Q, for Q1. And then this is, the second one's going to go up. Q2 goes up by a factor of 4. But then on the denominator, you're going to have that go up by a factor of 2 squared. So if that's the case, the numerator goes up by 8. The denominator goes up by 4. So the whole thing should be twice as much. So I think you have an answer of 200 newtons, be the case 3 answer. Okay. Moving along. Case number 4. Q1 is 10Q, 2Q is 20 times Q, and then you have a distance of 4. So our force now, F prime, I keep calling it prime, that would be the new force. The first one goes up by a factor of 10. The second one goes up by a factor of 20. So it looks to me like the top part of the fraction, the numerator, is going to go up by 10 times 20 or 200. And then the numerator is going to go up by 4 squared. So you're going to have 200 divided by 16. And so if you take 200 over 16 times 100, that'll give you your answer for F, the new force, which I'm calling F prime. Oh, we've got to get that in the screen. And if you do that, I believe your answer is 1,250 newtons of force. So that was case 4. Case 5, we talked about this before we left. How about if you have these situations where you take these Q1 and Q2 and change them, but you take those two conductors, bring them together, touch them, and then separate them. Okay, in this case, the force, if you touch them and separate them, you have to share the charge between those. So it's 10Q and 20Q. When they come together, I think they're going to neutralize 10 positives with 10 of the negatives. So their total charge afterward ought to be minus 10Q. So the charge on each is going to be minus 5Q. So then you could do the problem and say that your force, the numerator, should go up by a factor of 5 for the first one and 5 for the second one, but the denominator ought to stay the same. So that's like a factor of 1. So if that's the case, then I think it's going to be increased by a factor of 25, which means your answer should be 25 times 100 or 2,500 newtons. So the answer to case 5 would be 2,500. Then the last one, when you do that, it's actually giving you numbers for the charges. 5 microcoulombs, negative 8 microcoulombs. Bring them together, touch them, and separate them and see what we got. Well, it asks you to do it before you touch them. So in this case, we're actually going to put in our numbers for K, Q1, Q2 over R squared. So if I give myself a little bit of space here, K is 9 times 10 to the 9th. The units of K are Newton meters squared over Coulomb squared. You've got 5 microcoulombs is 10 to the negative 6. Then you have negative 8 microcoulombs, 8 times 10 to the negative 6. And then we're going to divide by, the distance here is 12 centimeters, so 0.12 meters, and we're going to square that. If you put all that together, I think your answer is 25 newtons. If you do the math on that, that's what you get. One of the two here, if you look up at the top, is positive and the other is a negative. So I think when you quote your answer on the bottom, you're going to say that force is attractive in nature. Okay? So that's before you touch them. So that's the answer to the first case. Now if I do the same thing, we talk about after we touch them. Our original case said we had 5 microcoulombs and negative 8. So when you touch them together, they're going to neutralize 5 of that 8. That's going to give us a total of negative 3 microcoulombs total. That means that on each, we ought to have negative 1.5 microcoulombs. So that's on each one. So if we do that and we find what is the force now, if we do K, Q1, Q2 over R squared, Coulomb's law, let's put in the numbers. We've got 9 times 10 to the 9th. Again, put in those units. You probably should get used to making sure that you do the cancellation, but you're going to have 1.5 times 10 to the negative 6th. And we're going to multiply by 1.5 times 10 to the negative 6 because they both have the same charge on each other. And then we're back to that same distance of 0.12 meters squared. You should see that the coulombs cancel, the meters squareds cancel, and all you're left with is newtons of force. But if you do the math on that, I got 1.41 newtons. The difference is that now, since they're both negative, that force will be repulsive. And what I think you should have learned in class is I don't normally have you put in the negative signs. I just think about it in terms of if you had two negatives, that they would exert repulsive forces on each other. Whereas in the other case, one was positive and the other was negative. And so that was attractive. So for the first case before, 25 newtons attractive. and then afterwards 1.41 newtons repulsive. Okay? If it helps and you haven't seen these problems before, maybe you should pause the video and try the problem before you take a look at the answers. But I hope this was useful. Stay safe. We'll see you next time.